Hello, this is Raymond. This is the newest episode of Ramblings with Raymond, and I'm again joined by my good friends and knowledgeable guests, Ed Kaczmarek and Pete Macler and George Hartay. And we're talking again about sand system design and development. And being a technical guy that never ran a foundry, there's lots of stuff I don't know. And so it was really fun for me to ask them questions like, how much sand do I need in my foundry? How do I get it off the truck? All of those kinds of questions. We talked about the sand system transport, the silos, and we talked some about shakeout. And so I hope you enjoy this episode as well. Please let us know if there are other topics or other guests you'd like us to interview. And we're going to continue to talk about sand. I think the next episode will probably look at cooler classifiers and thermal reclamation or reclamation systems, and that'll be fun as well. So I hope you enjoy this episode and look forward to doing the next episode with them very soon. Please let us know if you have any questions or any comments so that we can address any concerns you have. Thank you. So we're going to do sand system, and I can tell you it's one of the areas of the foundry I know the least about. I know really tiny little nuggets of things about the sand system, but not very much. And so I'm looking forward to understanding the sand system a lot better. So I was just trying to calculate, if I'm a small stainless shop and I make 100 man hours a ton, and there are 200 hours I'm going to work in a month, that means I need 2 people for every ton. If I did 50 people, I'm making 100 tons a month. If I did the math right. So
that's correct.
100 tons a month. How much sand do I need to make 100 tons a month?
What are you casting?
Stainless
iron, steel,
stainless steel pumps and valves in a small induction shop.
All right. What kind of molding method? No bake?
No bake. Nobody green sands anymore. No bake. I have no bake mixers, but I'm relatively manual, so I don't have an IMF line or anything. So I've got a very traditional 50-man kind of shop.
Okay, what I would assume a couple of things and then derive it from that. One, our sand to metal ratio is the first thing we need to know. Now that can range. Some shops I have at 1.5, or some other shops 6-1. So let's throw out a dart, 3-1.
Oh, I would make it bigger than that because I'm making pumps and valves. I'd make it 5-1, sure.
That's pretty radical. I've seen pump shops do that. Okay, but okay, pick a number, 4, let's say.
Okay,
4-1 sand to metal. What's your metal yield per ton? Are you getting 50%, 40%?
Oh no. If I'm making pumps and valves, if I ship 35 pounds for every 100 pounds I make, I'm doing well.
Okay. So we got 35% yield. So I'm going to say that we've got to make 12 tons of sand for each ton of castings based on those 2 factors. Now, I haven't put in scrap or anything else.
Sure.
But you do have to put in scrap. Let's say 5%, then that number might be a little different. But does that make sense? 12 tons, order of magnitude 12 tons of sand per ton of castings.
Yeah, and I'll make scrap. So let's make it 15 tons.
Okay. For planning purposes, that's a good idea to have a little bit of cushion. Yeah.
Sure.
So that's how I would approach it. Right.
Yeah, so how much sand in total do I need to have 15 tons of sand per ton?
How many tons a month are we going to produce? 100?
100 in a month, yeah.
All right, so it's that 15,000 tons of sand is what you're going to process. Let's say you want to divide that by 20 just for the heck of it. That would be 7,500, 750 tons in if you're out in the boondocks, you got to have enough sand to allow for the delivery time of new sand. So let's say you can get sand in a day or two. I would not have over a day's worth of sand, frankly, if it were my shop, if you have a proper cooler.
Sure.
A proper sand preparation and cooling, a day's worth of sand plus if you're using maybe 5 to 10% new sand, whatever your number is, I would have a couple of days.
I would think in that shop you'd probably be closer to 10 than 5.
Yeah, and on that shape, you'd bring in maybe a 30, 40-ton silo, so you could take a full truckload in one blast. They bring in 21 tons, so you'd want to have enough capacity in your new sand silo to take a full truck and also have something in there to begin with. So you're probably looking at 40 tons of sand in your new sand silo.
Okay.
Plus a full day of, let's call it mechanically reclaimed sand at that point. And if you want to get into thermal, you'd have another sand silo for the thermal, tap out of your mechanically reclaimed silo, run your thermal 24/7. And go into your thermally reclaimed silo.
So if I'm making green sand molds, and this is where Ed and George are going to have a lot of opinions, I'm sure, I'm going to make 5 times as many castings with those 50 people, basically. I'm going to be 20 man-hours a ton, not 100 man-hours a ton. So I'm going to make
in pumps, that would be pretty good. In pumps and valves, that's pretty good.
Right.
I'd say in commercial castings, piece of cake, that's doable.
We would use about 100 tons a day, and the main silo that we fed off of was a 150-ton silo. So basically we had a half day's cushion, and we were 90 miles away from the sand source.
Okay, when you did that, how many tons a month were you making typically?
About 1,000.
Okay, that's what I would guess. So 100 tons of sand a day, 150 tons in the silo, and you're making 1,000 tons a month.
Yeah.
How does that fit with you, Ed, in terms of your background at Spokane and even at Grady?
Well, the silos, so Peter's describing having basically 3 silos, a new sand silo, a mechanically reclaimed silo, and a thermally reclaimed silo. A lot of people do that now. I mean, that's become much more, reclamation is a lot more common than perhaps it used to be, that type. And so you're running a continuous process, and I think the thought process of how much to have is all reasonable. I think on your new sand, you want to be able to get a full truckload delivery. You don't want to run it too low. The interesting thing there is that even with anti-segregation, if you run silos really low, I've seen you basically get into your poor distributions even with anti-segregation systems. So basically, you don't want to run a silo dry.
Right.
So, all those are considerations on silo height.
How do you know how much sand is left in the silo? Do you monitor that? Is that just an accounting gimmick, or do you have somebody go look in the hole? How do you know how much sand is in a silo?
We had sensors in ours.
Yeah.
I've seen them all. I've seen people go and look. I've seen people with cranks that you lower that go down to see how low it is. I've seen sound systems. I mean, there's a whole variety of different ways, but for my part, I'll say I really always took that seriously. Strange things can happen when you think you got your silo under control, and all of a sudden you find out, why don't we have any sand today?
Wow. Wait, when you use sensors, George, what kind of sensors did you use? And I'm sure you tried 3 or 4 different ones and have an opinion about it.
We tried, first of all, something really easy. They make them for grain silos for farmers. It's just a little plunger button, and when it pops out, the light goes on that it's below that level. Those worked almost sometimes. And then we went to the other end and we tried ultrasonics, and those worked a little better. But what we actually wound up doing was putting actual probes through the electronic probes to the side of the tank, and that worked.
Okay. Wow. Wow. So that's how you looked at the level in it. Is contamination of your sand system, where does the contamination come from? Is that a reclamation, or do you get contamination with a new sand, or is contamination not something you have to worry about?
A and B, you never don't worry about it
Okay.
because it will happen.
Okay.
I think I explained the diamonds in another podcast we talked about.
Yep.
In the bottom of the heater cooler.
We did talk about some things like that in a past session, but I agree you can't take that for granted. You'd be surprised how many dead birds I've come across. And trying to resolve whether they came in the truckload of sand or whether somehow they got in. I mean, that happens.
Yeah.
Should it? No. Does it? Yes.
Wow. How did you unload and transport the sand? I've seen belts. I've heard people talk about pneumatic. I've seen sand pumps. How did you move sand around? How did you empty the trucks?
That was a pneumatic system. And like I think I explained before, we used shop air so that we could control the pressure, and we put the regulator in a locked box so the truck driver couldn't turn the pressures up. It was enough to get the sand out of the truck into the silo, but it minimized tearing up all the other equipment and ruining the sand in the process. Now, if you're going to run reclamation, you have a little bit better control if you use dense phase, which you're moving a slug of sand through the pipe rather than blowing it. They're a little more expensive, but they do a lot better job. I could never figure out how to put a dense phase system in with new sand delivery, because in essence, you have to put it in a pit.
Right.
And anytime you're putting something in a pit, stuff falls off the truck. And where we lived in winter, there's snow, ice, junk falling off. So I could never try to engineer around that to get dense phase for the new sand delivery. But anything that we moved in-house, we used dense phase.
Yeah, everything George said, I'm all on track with that. In addition to, I would add that just a little more detail on pipes. If you're transferring sand in some pneumatic system, then pipe wear and blowing out in elbows can happen. And so how you design a system, which of course is Peter's baby, how to work around that is more important than someone might think. And you can go for a long time depending on how much you're moving, and then all of a sudden one day you have a big problem and you never even thought about it until that happened, and then it's a big surprise. That was all regarding primarily new sand. There's more of a variety of ways to move reclaimed sand, return sand, and those types of things. There it's more often belts and buckets and things like that than it is to do it pneumatically.
So Peter, on pneumatic moving, I've got a place where I need to turn the sand. I'd use an elbow. I'm going to burn it out at some point. How do I decide how to avoid consuming that elbow too frequently? And how do I monitor it to know when to replace it rather than let it blow out?
Good questions. First, dense phase transportation has been around quite a while. The first system I ever put in was at Ford Motor Company in 1976, and it was a dense phase transporter. So that technology is proven. There's been a further step, though. Now there's called full line transport, where not only is it dense phase, but the pipe is never empty. So you start with a full pipe, you end with a full pipe, and you get away from the acceleration, deceleration of that empty pipe at the beginning when it blasts through, or the end. Even with a dense phase, you get that blast through at first and blast at the end. The full line technology, you don't. So I put a full line system into a shell molding shop, and we were transporting coated shell sand with dense phase We tested the sand for tensile strength versus brand new sand that wasn't transported. We could see no discernible difference going through the full line system versus getting the sand out of a bag. We had the same tensile strength. So the full line is a big step further than even dense phase. So you may not replace an elbow for a couple of years rather than every month with a full line system. I highly recommend that. There's a couple of approaches. One is the burp, where they give you slugs in the pipe. I can't mention names of companies, you know what I'm talking about. And the other, the whole pipe is filled and they have boosters along the way. Those are the two ways of getting a full line system. They're more expensive initially, but when you get all that maintenance on the pipes, they're a benefit and you won't be shut down as often. So I highly recommend the full line system.
Oh, wow.
On your elbow question, Raymond, we tried Nyhard elbows and they held up a little bit better, but we found there was an elbow that had a stop coming off the end that would fill with sand.
Right.
So as it went around the corner, it was hitting sand rather than the elbow of the pipe. And those held up usually over 2 years.
Wow. Wow. So for you, it was just a routine maintenance, look at it kind of thing. Did you ever do ultrasonics or something to measure how much thickness you had left on the elbow?
Oh.
Maybe we should have, but never did.
Oh.
Yeah, I mean, that was just the engineer in me came out and I said, yeah, how would I know that elbow's about to wear out? Well, I could use ultrasonics, see how much thickness I had left.
When we would take them down after 2 years or a little bit longer, there was about a quarter of it left from its original thickness.
Now, segregation we talked about before, and the truck itself is going to segregate when it's transporting the sand. So do you do something to remix the sand when you unload the new sand, or do you just live with that the first time through, or how do you handle segregation of the new sand coming in?
That's taken care of in the delivery system because it's pretty violent.
Oh, okay.
Unless you've got dense phase. And I think we talked about anti-segregation systems in your tanks.
Sure.
But the important thing that I can't stress enough is that on a regular basis, and we used to take ours down twice a year, you empty the tanks, you look at the slide gates, you look at the anti-segregation systems, make sure nothing's plugged up, make sure that you don't have any dead birds in there plugging something up. Because, yeah, we have those too. God only knows where the heck they come from. But if you just put that system in, and you say, this is going to work, and you don't take it down and inspect it and maintain it, it's not going to work.
I'm on track with all that too. Boy, George is just bailing me out here. I don't have to do anything today.
In most foundries, you see little bits of sand everywhere. What do you do about leakage, and how big of a problem is leakage in the system? And is that a daily maintenance item? Is there some bigger picture that I'm missing in terms of leakage or dust collection?
Very early in my career, someone explained to me, never walk through a pile of sand on the floor because it's going to get covered with what's coming from above.
Right. I'd like to add a point here. I think when you do have a proper pneumatic system that's well maintained, it's a clean shop. You shouldn't have spurts of sand coming out of that normally. That's unusual.
The pneumatic part of the system, yeah, that was pretty unusual.
Yeah, so I guess we get down to, if this is a large green sand shop and you're pumping hundreds of tons of sand, maybe 100 tons an hour of sand, or a couple hundred tons of sand an hour, that's going to be a belt or something along that line. You're not going to pneumatically transport that. And anyway, if it has clay bond in it, unless it's extremely dry, you're not going to be able to pneumatically transport it. Sure. I have foundries that do it, but it has to be very dry or it'll plug up very quickly. But that's a belt job. Now on belts, I like trough belts with covers. Trough belts tend to leak less along the edges than flat belts, even with the covers. And I like belts that are joined together with a vulcanized connection rather than a metallic hinge type connection. And those are a couple of things, just a couple of things you can do which will improve it. So
Well, that's great. Yeah, we have so few relatively high production shops, and green sand's really almost completely relegated now to railroad shops. So it's not that typical for us to do that. We're more concerned. And so I'm going to skip over mixers and molds and cores because I think those all go together, and that's a different discussion completely. But I would like to come back and look at shakeout and reclamation while we're just talking about sand system in total. One of the things that was told to me with a foundry that put in a new chemically bonded sand automatic system, when they put it in, the people who did the engineering work, one of the big firms that did the engineering work, asked them for the distribution of the size of castings they made. So they gave them the distribution and they designed the system so that it was capable of handling the largest castings they made, but was designed for the midpoint, or about 75% of the midpoint, thinking that one of those big castings would come down a day and it wouldn't be a big deal. Well, the production schedule in the foundry was never that I made one of those. When I made them all day and actually beat the crap out of that table. So they had to re-engineer the table. So one of the questions I have, just in wandering around, a lot of people in smaller castings now use drums as a way of separating the castings from the mold and moving that along. We still see a lot of tables, and the table shakeout area is always a challenging area in the foundry. For dust collection, it's challenging ergonomically for people to separate the castings from things. People use manipulators to try and pick up the castings after they're shaken out. Dust collection's always a mess. That's where you end up with a lot of the silica exposure. How do I understand? I mean, even when I started, Maynard had put in a dog house to try and prevent any of that crap from getting into the rest of the foundry. How do I manage the shakeout area, and what kind of equipment do I need? How big of a table do I need? How do I size the table for a shakeout system?
Ours was big. We had twin 75-ton decks and 300 horsepower motor on each deck. That being said, that would handle the 110,000 pound casting plus the risers. But the smaller pieces that we made, like on a half gear or a quarter gear, because it's not all flat on the bottom, where the splits are, it is raised. So that would fall down on the deck and just get hammered. So we actually had to put pads on some of the stuff that we knew were going to get hammered down. And the smaller parts, you couldn't leave them. If somebody left them on there too long, they'd get beat up.
Sure.
It was just the nature of the beast. We had the doghouse also for dust collection. And then we had to add a movable top because we had, I think it was 6 200 horsepower fans on there, but it would still overpower it. There was too much stuff coming off. So we had to put a deck over the top. It was a metal roll that came on and off.
Did you design, George, to have a constant airflow through the plant? I mean, I've been in plants where you can't open the door because they don't have enough air supply. You find that in restaurants sometimes too. How did you manage that whole airflow through the plant?
We had huge makeup air units on the roof.
Wow.
And they were also gas fired so we wouldn't freeze everybody in winter.
Oh,
that's the proper way to do it. That is a good design. Yep.
And those were sized to balance out whatever we were sucking out. So you had pretty even airflow.
So Ed, what did you do? You were in Milwaukee and then you were out in Spokane. How did you manage the shakeout area? How big was your shakeout? How much power? And then I'm going to dump on Peter that little stainless shop we've been talking about.
There was a variety of systems, a variety of different lines feeding into different shakeout systems, even within each of those plants. And no two of them were the same because they tend to be legacy systems. So how old is the legacy? And, they all work, but they all have the risk of being dusty and beating the castings up, and systems tend to get designed for whatever parameter went into the original design. Peter hears this all the time, I'm sure. But everywhere I've gone, the system already exists, and whatever the design parameters that were given for when it was installed got abandoned long ago as new product lines came along, or the opportunity came up to, or perceived good opportunity to make heavier castings or more frequent castings or different alloy. And all of a sudden, whatever the good design was, well-designed system, now you're pushing that system. And that's just something you figure out how to work around. And it's not always pleasant.
Some of my members have routinely told me that when you buy a new piece of equipment, it ordinarily can be relatively well designed for the parameters you put forward, but you really quickly run into limitations. So a number of my members re-engineer their equipment every time they have a failure. They see a failure in the equipment. They don't just buy the replacement part from they don't go down to the industrial warehouse and just replace it. They look at that as an engineering failure and try to upgrade every piece of equipment in their facility every time they have a maintenance failure. They don't see it just as a maintenance item. Was that a strategy both of you used in terms of equipment failures or maintenance issues?
Yeah, we had our own big engineering department, and we had plant engineering, and anything that failed would be automatically upgraded. And anything that we bought that had a drive on it that failed, we would put our own drives on.
Well, you're the experts on that, George.
Well, and that's, I think, a logical way to approach it and the most common. However, sometimes I would take a look at, what the failure was, and were we just asking this equipment to do more than it was ever going to be capable of doing? Because wherever the failure point was this time, we could make that a little bit more robust and say, now we're going to redesign it to handle X bigger.
Yeah.
Except that 2 weeks later, the next point in the failure chain is going to fail. So you either have to have a really comprehensive engineering area, or sometimes it was just easier to take a step back and say, wait a minute, we're getting a failure here because we're trying to make this part and it just doesn't fit on this line. And can we put it on a different line? Do we really want to make this part? Or are we willing to really put in the engineering time to really look at the system, and not only what is going to keep us from having the same failure again on this specific piece of equipment, but what's the next failure point in the chain? And we might as well anticipate that that's the next one that's going to go.
Peter, two different kinds of questions. One is they've both been in relatively large industrial equipment, not small, no-bake shops. When I'm looking at a foundry, what's the driver on how big a shakeout table is? Is it the weight of the casting, the number of castings? Is it the horsepower of the engines? What is it that drives the decision on a shakeout operation?
Well, there's usually two big ones. One is the weight, obviously, and you're going to set not only the casting on, you're going to set a complete mold on. The days of knocking out the castings on the floor and then bobcatting into the shakeout are over now with OSHA. Every big system I've designed, we have the entire mold go into the shakeout. The shakeout is completely enclosed in a house, and the house is movable off to load it on when you start it up, so you have 100% closure before you start the shakeout.
Sure.
All right, so you've got the mold weight, the casting weight. Maybe you may even have a flask under you want to rattle before you lift the flask out. So you've got a lot of weight you've got to consider on that. Then, of course, there's simply the dimensions. So you've got a 10-foot by 10-foot mold. Well, the shakeout's got to be substantially larger, because when that sand starts to fall away, it's going to tumble at probably a 45-degree angle. So that might be a 15-foot square, 16-foot square table to keep everything contained.
Okay.
So the size, in terms of volume, well, we can do a system that'll take 50 tons an hour or more, and there are systems like that. That depends on how fast you can break the molds down.
Sure.
Not only how fast you feed them in, but if you can't process them, you're not going to do it. I was vice president of Luke & Steel, a Simplicity Engineering division that made shakeouts, okay? That was in the 80s, and we made shakeouts that were huge and small ones and all sizes. So for very large castings, you're kind of stuck with a brute force type of unit, which is not a natural frequency unit. You need a hard hammer hitting that mold to break it down. You can do it with natural frequency, but it's going to take a long time. It doesn't have the power. And the old brute force units had a crank on it, an exact stroke every time, 3/4 of an inch at 750 RPM. I can remember it. And that was your optimum stroke for a brute force, 3/4 inch at 750 RPM. You had to hammer it hard to break the molds down. Otherwise, it'd sit there for half a day breaking down.
Wow.
So touching on the barrel type shakeout versus
Sure.
the vibrating drum type shakeout, one of the large auto manufacturers contracted me to move their malleable foundry from one location to another, and they wanted to put a shakeout in. And the question is it going to be conventional, a drum, or a vibrating drum, a rotary drum or a vibrating drum? So I contacted both the manufacturers of those machines. We sent 5 tons each of tons of castings to them, and we ran them through those machines. Turned out the rotary drum, no flaws, no cracks, and the castings were the cleanest between those two systems. On this one only, I'm not saying it's for everyone, but on this particular application on green malleable castings, the rotary drum did a better cleaning job and broke 0 castings in the process. So that's what we selected based on a test. And I think that's the logical way to go if you can.
Yeah, it does seem like, if I look around, that rotary drums have found a niche in the market. They're not a complete replacement for the table, but certainly people know how to use those. Yes,
I see lots and lots of those in iron shops.
Yeah, no,
I don't know that I've seen any in the steel shop.
Yes, I have a client that has 2 of them, and they're done. And they also, when you get back to aluminum, it's another story, because you can ding up aluminum pretty easily in the process. If you've really engineered that system well and you've got exactly the right flow, you can do aluminum in the rotary drum. You got to be careful. If the castings start to tumble inside, you're going to ding them up. But that's rotation, RPM, inclination of the drum, depth of media. You got to put all that together and hit it right, and you can do aluminum just fine.
Yeah, one of the funny things with the rotary drum is a lot of times they set up the gating system so things break off.
Mm-hmm.
And then the stuff that breaks off helps you get the cleaning action. So I've seen people that cast balls on the side of the gating system. So in the drum, the balls break off and help clean the casting off. So,
good idea.
Yeah.
I want to touch base and back up just a tad. We talked about sand segregation. Sure. One of my clients, and you're familiar with this client, Raymond,
sure,
thermally reclaims all their sand, including the new incoming sand, before they use it.
Sure.
And in doing so, they get rid of fines, which is a good idea. long before it gets into the system. If you just blow it into the silo, even though you've got sand segregation, your fines are going to be higher because you blew it in.
So would
Well,
if you had the capacity, would you
yeah.
bring your sand in through the cooling classifier rather than directly into the new sand just to get rid of the fines?
Well, that would work. No question. But there are also another benefit. They believe that they had a little more thermal stability in the sand once it went through the thermal reclaimer.
Oh, I think there's no question about that. The thermal reclamation does give you more thermal stability. If you get it up into those high temperatures, there are places in the sand that want to break off, so you create fines. There's also places in the sand that really want to be cristobalite or high temperature quartz. And so, yeah, if you put it through that, they've gone through the transformation, they're not going to transform back. And so you lose some of that dimensional instability and instability in the sand system with a pre-treatment.
Well, that was their reason for doing it. Those twofold. Not only was it to remove fines, but to develop a greater thermal stability in the sand. In a smaller shop, that's not a bad deal. In a huge shop, it might be quite expensive to make all that happen. I understand that.
Yeah, and when you're only adding 5% new sand and you're using mainly reclaimed sand, people have found that when they have to make a mold out of completely new sand, they have dimensional instabilities they don't have when they have the reclaimed sand. So there's a pretty good bit of information. I know, George, how much of your sand was reclaimed? Did you use all new sand facing or did you?
Facing.
Okay.
In regards to your new sand, it can also lead, if you haven't transformed that sand, it not only has dimensional issues, but you can have big hot tearing issues. Because
Right.
if you do the work, that sand grain expands 30%. So I had friends in the industry call me, say, hey, we've switched to no bake with ABC binder, and we were green sand. We never had a hot tear problem.
Right.
And now I got hot tears coming out of my ears. And I would say, are you using all new sand? They would say yes. And I would explain it to them. And, until they got enough sand in their system and got their reclamation up, there's not a whole hell of a lot you can do about it. People talk about collapsibility and this and that. You cannot overcome that because the temperature at which the casting wants to contract is the same temperature that sand is expanding, and it's going to kill you.
Yeah, George, you've always been really good at pointing out that challenge that we face with the expansion of silica sand and the opportunity to even use some of the specialty sands just to reduce hot tearing. And so it's something that I've routinely recommended, where you've got even risers, and between the risers you may have enough plain silica sand expanding to cause hot tearing, and if you just put some of the specialty sands in there, you can reduce that dramatically.
Well, another thing, Raymond, that if you're using a round grain sand, you have no slip planes. I mean, it's rock on rock. If you're using a subangular sand, you have slip planes, so you're less apt to get hot tear. The other thing people do is make molds that are too strong. Too strong. People say, well, it can't be too strong. Yes, it can. If you want hot tear, make it too strong. If you want to try to put some subangular sand in, you'll have a slip plane where that movement can occur with less damage.
That's an interesting compromise, and so that'll be an interesting aside discussion right now. In lost foam, we wanted to use in Saturn for aluminum and iron the same sand for aluminum and iron. And in lost foam, the sand needed to flow. So a round grain sand was wonderful. You could get it to fill all the holes. But in iron castings, in the bottom of the mold, where there was still a little bit of movement, we had penetration. So one of the intuitions we had was the angular and subangular grains would have more mechanical interaction, so that you'd actually, in unbonded sand, when you densified it, you'd have more resistance to penetration and movement in subangular than in round grain sand. But the round grain sand would allow you to fill it more. One of the things we haven't talked about, we'll talk about in molding, is in lost foam, if you vibrate while you're filling, your sand mold is about 10% denser than it is if you don't vibrate while you're filling. And so that was one way of getting more dense sands, but density of the sand, more than just the binder strength, is probably one of the main drivers in the hot tearing problem.
Yeah.
More sand in the hole rather than more glue between the sand.
Do you see more permeability issues if you have a denser mold as well?
Yes. You have more permeability issues, and the angular sands give you lower permeabilities. And so that was the kind of trade-offs we saw, was the angular sand in an unbonded sand system gave you greater strength and resistance because you couldn't flow past each other, but it did decrease the permeability and increase the sort of hot tearing potential. But permeability in lost foam was always just a mistaken understanding because you're really trying to get a plastic goo out. And so having enough capillary action at that mold metal interface is really key. And so one of the ironies was they always wanted the low permeability coating in aluminum castings, but that was primarily because the low permeability castings had clay in them, and the clay was great at soaking up that organic goo you were trying to push through it. And so that worked really well in aluminum. In iron castings, you needed a coating that was highly permeable, because when you're pouring something at 2,600 degrees, then you pop all those organic molecules apart and you got to get rid of all that gas. So that was pretty interesting.
I was involved with the General Motors Messina project, the lost foam up there.
Wow.
I had the sand system was I was working for another company at the time, but that was my project to do that one.
Wow. I knew the Messina guys when I was at Saturn Corporation. They were some of our key folks. It was the next generation. It wasn't the people who installed it originally, but they were really bright and clever. They were good folks to work with. They'd spent a lot of time on that. I hope you enjoyed this episode as well. And once again, I really invite you to send your comments, your criticisms, your suggestions for us. We really want to service the people who watch these podcasts and really talk about the subjects they're most interested in. So thanks for watching and hope you enjoyed it. Thank you.